So good day everyone. So today we're gonna tackle all about three different theorem in the number theory. So first is a Chinese remainder theorem. Second is a Fermat Little theorem. And the last one is a Euler's theorem. So let's get into the video. So Chinese remainder theorem. So the origin of Chinese remainder theorem was first developed in the 3rd century AD by Chinese mathematician Sun Chu. Unfortunately, not the same as his more famous countryman who authored The Art of War and republished in a 1247 book by Qin Jiu Shao titled Mathematical Treatise in 9 sections. And Chinese remainder theorem is the only theorem that applies in modular arithmetic. Specifically, when we have the relationship x equals k mod g, where x minus k equals some number which is a multiple of g. So just like for example, 38 is equal to 14 mod 12. So we can see then that k is broken up into multiple classes with any given k plus divided by negative g. And these are some example and techniques of modular. So what the heck is it? Well, first, you need a set of numbers that are pairwise co-prime integers, such as 9, 10, 19, or 10, 7, 33, and 13. So that is a set of numbers that when paired are only divisible by 1 is to 9 and 10, or 33 or 13. So the theorem states, which is the Chinese remainder theorem, that any set of these integers n1 and n2 is to nk, and any given integers a1, a2, and so on until ak, so there exists an x such that x equals a1 mod n1 and x equals a2 mod n2 and x equals ak mod nk. So there is a sample problem. So just by knowing the truth of the theorem, can you figure out that x must be in a system. So x equals 2 mod 3, x equals 3 mod 4, and x equals 1 mod 5. And the simplest proof that is that x equals 2 mod 5 gives x equals 5k plus 2, and x equals 1 mod 11, and x equals 4 mod 19. So x equals 5k plus 2 equals 1, and mod 11, so 5k equals to negative 1 mod 11, which via equivalence classes is 5k equals 10 mod 11. Thus, k equals 5 mod 11. So, k equals 11g plus 2, and thus x equals 5 quantity 11g plus 2 quantity plus 2, and thus x equals 5 close and open 11g plus 12 is equal to 4 mod 19. So 5 times 11 times g is equal to negative 8 mod 19. So 5 times 11 times g equals 11 mod 19. So 5g is equal to 1 mod 19, and g equals to 4 mod 19. 4 times 5 minus 1 is equal to 19. So g equals 19m plus 4, and so x equals 5 times 11 times 19m plus 5 times 11 times 4 plus 12. And that's the Chinese remainder theorem. And now, let's proceed to Fermat-Lettel theorem. Fermat theorem. So if p is prime and a is an integer not divisible by p, then p minus 1 is congruent to 1 mod p. And for every integer p is congruent to a mod p. So this theorem is also known as Fermat-Lettel theorem, that used in a public key RSA and primality testing. Consider a set of positive integer less than p, 1, 2, 3, and quantity p minus 1, and multiply each element by a and modulo p to get the set. So x is equal to a mod p and 2a mod p times the quantity of p minus 1 a mod p. So no element of x is 0 and equal since p doesn't divide a. And multiplying the numbers in both sets, p and x, and taking the result mod p yields. So a times 2a times the quantity of p minus 1 times a is congruent to 1 times 2 times 3 and the quantity of p minus 1 mod p. So a raised to the power of p minus 1 times the quantity of p minus 1 factorial congruent to quantity p minus 1 factorial mod p. Thus, on equating the quantity of p minus 1 factorial term from both the sides, since it is relatively prime to p, the result becomes a raised to the power of p minus 1 congruent to 1 mod p. And as an alternative form of Fermat's theorem, it is given as a raised to the power of p is congruent to a mod p. So if p is a prime and GCD quantity a times p is equal to 1, then a raised to the power of p minus 1 is congruent to 1 mod p. So examples, 2 raised to the power of 2 is equal to 1 mod 3, and 6 raised to the power of 4 is equal to 1 mod. Last is 3 raised to the power of 2000 mod 19. So the converse when a is equal to 2 usually holds. Fermat, if b is a prime and doesn't divide a, so a raised to the power of p minus 1 is congruent to 1 mod p. And in converse, if a raised to the power of p minus 1 is congruent to 1 mod p, then p is prime and doesn't divide a. And this is almost always true when a is equal to 2. Rare counterexamples. And if n is equal to 561, so it is equal to 3 times 11 times 17, but 2 raised to the power of 560 is congruent to 1 mod 561. So n is equal to 1729 equal to 7 times 13 times 19. Primality testing scheme typically use the contrapositive of Fermat. So even we use Fermat as a filter since it's faster than factoring if calculated using the power mode, and divide by other primes. And Fermat p prime is raised to the power of 2 raised to the power of p minus 1 is congruent to 1 mod p. Contrapositive? So yes. And why can't we just compute 2 raised to the power of n minus 1 mod n using Fermat if it's so much faster? Because prime by factoring and advanced technology is yes, it's prime. So now let's proceed to the last theorem, which is the Euler theorem. Euler totient function. So null set of n is to how many numbers there are between 1 and n minus 1 that are relatively prime to n. So for example, null set of 4 is equal to 2, then to the quantity of 1 and 3 are relatively prime to 4. A null set of 5 equal to 4, to the quantity of 1, 2, 3, and 4 that are relatively prime to 5. And a null set of 6 is equal to 2 times 2 to the quantity of 1 and 5 that are relatively prime to 6. And a null set of 7 is equal to 6 times the quantity of 1, 2, 3, 4, 5, and 6 that are relatively prime to 7. And from null set of 5 and null set of 7, the null set of n will be n minus 1 whenever n is a prime number. This implies the null set of n will be easy to calculate when n has exactly two different prime factors. So null set the quantity of p times q is equal to quantity of p minus 1 times quantity of q minus 1, and if p and q are prime. If GCD, so the quantity of a and p, is equal to 1 and a is less than p, then the null set is congruent to a raised to the power of p times 1 mod p. In other words, if a and p are relatively prime with being a small integer, then when we multiply a with itself to the null set p times and divide the result by p, which is the remainder will be 1. So the statement for every a and n that are relatively prime, so a, the null set of n, is congruent to 1 mod n. And above equation is true that if n is prime, because then null set of n is equal to n minus 1. And Fermat theorem holds, and consider the set of such integers labeled as r is equal to x sub 1 and x sub 2 and so on until x into the null set of n. And here each element x of r is a unique positive integer less than n with GCD x in n is equal to 1. And multiply each element by a modulo n, and the set S is a permutation of R because a and x is relatively prime to n, so a must also be relatively prime to n. Thus, the elements of S are integers that are less than n and that are relatively prime to n, and there are no duplicates in S. And both Fermat and Euler theorem plays an important role in a public key cryptography or RSA and used in periodic decimal expansion. And here are some examples. So choose two large prime numbers p and q. So let p is equal to 7 and q equals to 17. So the next is calculate n is equal to p times q. Thus, n is equal to 7 times 17 is equal to 119. The next step is to select the public key or the encryption key or E such that is not a factor of p minus 1 times the quantity of q minus 1. So now, 7 minus 1 times the quantity of 17 minus 1 is equal to 6 times 16 equals to 96. So factors of 96 are 2 and 3. So 2 times 2 times 2 times 2 times 2 times 3. So E has to be prime to 96 and let E is equal to 5. The next step is to select the private key, which is the decryption key, D such that the following equation is true. So D times E mod P minus 1 times the quantity of Q minus 1 is equal to 1. So substitute the values of E, P, and Q in the equation. So let's choose D is equal to 77. Since 5 times 77 mod 96 is equal to 385 mod 96 equals to 1, which satisfies the above condition. So next, for encryption, calculate the ciphertext or CT from the plain text PT as follows. So Ct is equals to Pt E mod n. So let us consider of encoding of alphabets as A is equal to 1, B is equal to 2, C is equal to 3, and Z is equal to 26. So we have to encrypt a single alphabet F equals to 6 using this scheme with B public key as 77, known to A and B's private key is 5, known only to B. So Ct is equal to Pt E mode 119 is equal to 6 raised to the power of 5. Mode 119 is equal to 41. And the next is to send Ct as a ciphertext to the receiver. So send 41 as a ciphertext to the receiver. So for the last step is to decryption at the server. Calculate the plain text Pt from the ciphertext Ct as follows. So Pt is equal to Ct raised to the power of d mod n. So Pt is equal to Ct raised to the power of d mod 119 is equal to 41 raised to the power of 77 mod 119 is equal to 6, which was the original plain text, so the code of F. So that's the three different theorem in a number theory.